Alrighty, so let's take a look at June 2014 multiple choice exam. So the first question shows how the force acting on a rocket varies with time. Which one of the following is represented by the area under the graph? The area under a force time graph is the impulse or the change in momentum, so that's going to be option D. A golf club strikes a stationary golf ball of mass 4.8 times 10 to the minus 2 kilos, and the ball leaves with a speed of 95. If the average force exerted is 7,800, how long are the ball and club intact? So we know that the force is going to be the rate of change of momentum. So if we want the change in time, it's going to be the change in momentum over the force, with the average force. So there's going to be 4.8 times 10 to the minus 2, so that's the mass, times 95 because it's gone from stationary, and that's divided by 7,800. So let's type that in. 4.8 times 10 to the minus 2 times 95 divided by 7,800 gives us 5.8 times 10 to the 1, 2, 3, 4. So that's going to be option A. Okay, so water of density 1,000 kilograms per meter cubed flows out a garden hose of cross-sectional area 7.2 times 10 to the minus 4 meters squared, at a rate of 2.0 times 10 to the minus 4 meters cubed per second. How much momentum is carried by the water leaving the hose per second? So we're trying to get to momentum per second. So that's going to be mass times by velocity per second, which is going to be volume per second times by density times by the velocity. So we haven't been given the velocity, so what we're going to do is generate velocity by dividing the volume per second by the area. So let's do that. So we've already got volume per second in there. We've got this, and what we're going to do is take volume per second again and divide it by the cross-sectional area there. So we end up with the volume per second squared times density divided by the cross-sectional area. So let's put some numbers in. So the volume is 2.0 times 10 to the power of minus 4 squared times by 1,000 divided by 7.2 times 10 to the power of minus 4. And that comes out as 0.055555, which is going to be 5.6 times 10 to the minus 2, which is option B. A model car moves in a circular path of radius 0.8 meters at an angular speed of pi/2 radians per second. What is its displacement from point P 6 seconds after passing P? So the first thing is its displacement, or its angular displacement, will be the angular speed, which is this one, times by 6.0, which is going to be 3 pi. So essentially, if it's for there, it's now going to be over here. So if it was 0.8 meters over here, it's now going to be minus 0.8 meters. From the origin, which is a change of 1.6 meters, which is option C here. So the key thing here was working out the angular displacement would be 3 pi, so that's going around 2 pi to the same position, and then pi to get to this position here, and that's going to be 2 radii, or 1.6 from it. A small mass is placed at P on a horizontal disk, which has its centre at O. The disk rotates anti-clockwise about a vertical axis through O with constant angular speed. Which one of the following describes the force which keeps the mass at rest relative to the disk when in the position shown? So if it's going in circular motion, there needs to be some kind of centripetal force, and friction is going to supply that. So essentially what we're going to have is a frictional force directed towards O to keep it in circular motion so it follows with the disk. 0.2 kilogram mass is whirled around a vertical circle on the end of a light string of length 0.90 meters. At the top of the circle, the speed of the mass is 8.2 meters per second. What is the tension in the string at this point? So if we look at this, when it's at the top, you've got obviously the tension pulling it in, but you also have its weight force. So we know that into its centripetal tension is going to be mv squared over r. In this case, we're going to subtract mg. So v squared is 8.2 squared divided by the radius, which is 0.90, minus 9.81, and times the whole lot by m, 0.20, gives you the tension, which is 12.98, blah, 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 which is essentially 13. So that's going to be answer B. Which line A to D in the table gives the amplitude and frequency of a body performing SHM whose displacement at x at time t is given by the equation x equals p cos qt? So the frequency, well, we know that q is going to be equal to 2 pi f. So we know that the frequency is q over 2 pi. So that eliminates that one and none of the others. And the amplitude is going to be this term, the p term. So that's essentially going to mean it's answer C. The tip of each prong of a tuning fork, emitting a note of 320 Hz, vibrates in SHM with amplitude 0.50 millimeters. What is the speed of each tip when its displacement is 0? So that is going to be essentially the Vmax, which is 2 pi f a. So it's going to be 320 times by 0.5 times 10 to the minus 3 times 2 times pi, which is 1.00 blah 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 meters per second, so times 10 to the power of 3 to go in millimeters. So 320 pi millimeters per second once you get the right units and put the right numbers in for that. Okay, so a periodic force is applied to a lightly damped object, causing the object to oscillate. The graph shows amplitude of the oscillations varies with the frequency of the periodic force. Which one of the following statements best describes how the shape of it would differ if the damping had been greater? So damping essentially causes this to happen. So the amplitude is reduced at all points. So we're looking for the curve to be lower at all the frequencies, which is that one, so we got that straight away. Spacecraft of mass m is at the midpoint between the centres of a planet of mass m1 and its moon of mass m2. The distance between the spacecraft and the centre of the planet is d. What is the magnitude of the resultant force on the spacecraft? Okay, so if it's at the midpoint, that means there's a distance d from the moon as well. So the force is going to be the force from the planet, which is that one, minus the force from the moon, and because it's, so we know it's that, so we can factorize that by taking out the gm over d squared m1 minus m2. So which one corresponds to that? So it's none of these plus ones, so it's not those two, and you're finding the one with d squared on the bottom, so that's going to be C. Which one of the following statements about gravitational potential is correct? Gravitational potential can have a positive value. Rubbish. They're all negative. Potential at the surface of the Earth is 0. Rubbish. It's not. If you put that into equation, that's obviously not correct. Gravitational potential gradient at a point is the same value as the field strength. Yes, the field strength is often known as the potential gradient. The unit of gravitational potential is newtons per kilogram. Rubbish, that's field strength. Which one of the following statements is correct? The force between two charged particles is always attractive. Rubbish, sometimes it's repulsive. Can be measured in coulombs per farad per meter. Possibly. Let's see if we can eliminate the other two. Is directly proportional to the distance between them? No. It's inversely proportional to the distance squared. The independent magnitude? No. It's not. It's dependent on the magnitude. So it must be this one here. So let's have a look at the equation just to double check. So force is QQ over 4 pi E0 R squared. So it's going to be Coulomb squared over 4 pi, which is unitless. Then we have E0, which we look on our formula sheet, has the units farads per meter. And then we're going to times that by meters squared. So we end up with C squared over FM, which is exactly what it's got there, so that's fine. 2 point charges, X and Y, exert a force F on each other when they are a distance D apart. When the distance between them is 20 millimeters, the force they exert on each other is 0.5 F. What is the distance D? So if we're at half the force, we must have essentially multiplied the distance squared by 2. So if we think, if we're F force is going to be QQ over constant times by D squared, therefore 0.5 F is going to be QQ over 2K D squared, which we can also write as QQ over K root 2D squared. So essentially what's happened is to go to 0.5 F, we've multiplied D by root 2, so to work backwards, so 20 divided by root 2 would give us what D is, and that comes out as 14.14 blah blah blah, so that's going to give you 14 millimeters. Which of the following statements is correct? When a negative ion is projected into an electric field, the field can change the magnitude of the velocity but not its direction. No, it can change both. It can change the direction but not its magnitude. Rubbish. Can change both. Yes, it can absolutely change both. There's no reason it couldn't. Okay, so let's move straight on. Two identical positive point charges, P and Q, are separated by a distance of 4 meters. The resulting electric potential at point M, which is midway between the charges, is 25 volts. What would be the resultant electric potential at a point 1 meter closer to P? So the potential from P would be K 2.0 to start with, and it will be exactly the same for Q, and we know that's equal to 25.0 volts. But now what we've got is P, if it's moved 1 meter close to P, 1 plus Q K times 3.0, and if they're identical, essentially P and Q are the same, so we can essentially write the top line as K 2.0, which is essentially P over K, and we can write this one as P over K plus P over 3K, which is 4P over 3K once you factorize it. So essentially what we've done is multiply by 4 over 3. 25 times 4 over 3 gives you 33.333, which is option C here. The diagram shows the field lines and equipotential lines around an isolated positive point charge. Which one of the following statements concerning work done is incorrect? When it is moved from either P to Q or S to R, the work done is the same in each case. Yeah, it's the same change in potential, so that's true. So it's not that answer, sorry. When it's moved from Q to R, no work is done. That's also true because it's on an equipotential line. When it's moved around the path PQRS, the overall work done is 0. So let's think about that there quickly. No, it's not going. It is going to be 0 because of the amount you put in to go from P to Q. You get back from R to S. When it's moved around the path PQRS, the overall work done is twice the work done. No, it's not, because the work done is in opposite directions. One, you're putting energy in, the other, you're getting energy out, so that one is not correct. 2 fixed parallel metal plates, X and Y, are at constant potentials of plus 100 and plus 70. An electron travelling from X to Y experiences a change of potential energy EP. Which line A to D in the table shows correctly the direction of the electrostatic force on the electron and the value of E change in potential energy? So the electron is negatively charged, so it is going to be essentially subject to a force to the left. So it's going to be towards X or away from Y. So it's neither of these two. So the final question to ask is whether it's essentially gaining or losing energy, because essentially that's what these two expressions have. So if we're moving away from the more strongly positive, so going against the force, we're going to be gaining potential energy because we're moving away from where it wants to move towards. So it's like moving an object up from the surface of the Earth. So that's going to mean we're gaining potential energy, which is that one. Okay, so question 18. A uniform electric field of field strength E is a line, so it's vertical. An ion moves vertically through a small distance, delta D, from point X to point Y. There is a uniform gravitational field strength of G throughout the region. So we're in a vertical direction. So which line A to D gives the correct gravitational potential difference and the electric potential difference between X and Y? So if the field lines are going that way, this is positive and this is negative. So remember that field strength is the potential gradient, therefore the potential will be the field strength times the change in the distance. So we're going to need two expressions with field strength times delta D, the distance effectively, which is both of these ones here. So we're going to need that one. So essentially we're using the fact that the field strength, E or G, is essentially the potential gradient like this, and just putting an R in for D. Initially, a charged capacitor stores 1,600 microjoules of energy. When the PD across it decreases by 2 volts, the energy stored becomes 4. So what you notice is the energy has has quartered here. So if we remember that energy is equal to half CV squared, so if the energy is quartered, that means that the potential difference has divided by 2, because then when you square it, you end up quartering. So the potential difference is halved by changing by 2.0, and the only number that essentially works for is the number 4. So the number 4 is the only number, if you subtract 2 and halve it, you get the same number. So that means initially, if the first one, the potential difference is 4, and then the second one, potential difference is 2 volts. So we can now put that into our equation. So let's do it for the first one. So 1600 times 10 to the minus 6 gives you microjoules, times 2 and divided by 4 squared, because that's the potential difference. And that gives you 2 times 10 to the minus 4, or 200 times 10 to the minus 6, which is option B here. A switch in the circuit is held in position 1, so that capacitor becomes fully charged to potential difference V and stores energy E. Switch is moved quickly to position 2, allowing C to discharge with a fixed resistor R. It takes 36 milliseconds for the potential difference across C to fall to V over 2. What period of time must elapse after the switch has moved to position 2 before the energy stored by C has fallen to E over 2? So remembering that the energy is directly proportional to the V squared, so if we're going to E over 16, essentially that must mean the potential difference has quartered. So it takes 36 milliseconds to halve, so it's going to take 2 sets of 36 milliseconds to quarter, so that's going to be 72 milliseconds. The path followed by an electron of momentum p carrying charge minus e, which enters a magnetic field at right angles in a circular arc of radius r. Well, will be the radius of the circular arc followed by an alpha particle of momentum 2p and charge 2e when it's in the same field at a right angle. So remember, what's happening here is your BQV is being equated to mv squared over r, which we can write as p squared over rm. But let's take the v across to the other side, like that, so we can cancel the squared with this mv here. So essentially what we end up with is bq is equal to momentum over r. And what we're trying to get is an expression for r, so it's going to be momentum over bq. So what we've done is we've got double the momentum, so that you've times 2 on the top line, and you've got double the charge, so you've times 2 on the bottom line, so you end up with exactly the same radius as before, so b. In which one of the following applications does electromagnetic induction not take place? Generators, that is electromagnetic induction. An AC power adapter, that is a transformer, so that does involve induction. The wings of an aircraft, that also induces an EMF, so that is induction. A backup capacitor, capacitors have nothing to do with induction. Capacitance is different to induction, so it's that one. When a magnet is dropped through an aluminium ring and an EMF is induced, a data logger connected to the ring records the variation in induced EMF with time as shown below. In a second experiment, the magnet is dropped from a greater height. Which one of the following graphs best represents the induced EMF in the second experiment? So if it's dropped from a greater height, it's going to be going at a greater velocity when it arrives. So essentially this whole thing should happen faster because it's travelling at a higher speed, and because the rate of flux cutting is going to be greater because it's travelling at a higher speed, we'd expect a larger EMF to be induced, and so we should have essentially the same peaks but with larger EMFs and a shorter time, which is this one here. So the peaks have got essentially higher, and then the time here is shorter, so it's D. A rectangular coil of area A has n turns of wire. The coil is in a uniform magnetic field as shown in the diagram. When the coil is rotated at constant frequency f about its axis xy, and an alternating EMF of peak value E0 is induced in it. What is the maximum value of magnetic flux linkage through the coil? So we know that the EMF is the rate of change of the flux linkage, like this, and we know it's at its peak when it's E0. So we can put in an expression for the EMF. It's BAN omega sine omega t, and that's going to be maximized when this is equal to 1. So BAN is the flux linkage, so essentially, you know, the flux linkage is going to be the maximum EMF, because we're going to make that 1, over omega, which is E0 over 2 pi f, which is option A. Transformer has 1150 turns on the primary coil and 500 turns on the secondary coil. The primary current is 0.26 and 230 volts AC. The current on the secondary side is 0.5 amps. What is the efficiency of the transformer? So, first of all, let's work out what the potential difference on the other side. So it's stepping down, so it's 1150 divided by 500, which is equal to 2.3. So it steps it down by a factor of 200.3. So we know the 2.3, so that you know the power out is going to be the current out, which is 0.50 times by 230 over 2.3, which is 100, divided by 0.26 times by 230. That gives you the power in, which gives you efficiency if you times it by 100. 0.5 times 100 divided by 0.26 times 230 gives you 83. 0.83 times by 100 gives you 83.6. So that's going to be 84%. And that concludes the 2014 paper.